Yesterday we covered our last bit of new material that we need to know for our unit exam on Monday, but also for our final exam coming up on the 26th. It was called the Doppler effect. The Doppler effect is a phenomenon whereby the apparent frequency, so the frequency of a sound that we hear, not the actual frequency of the sound, but the frequency of the sound that we perceive seems to be higher or lower than the actual frequency. So the apparent frequency is different than the real frequency. Now, why is that the case? Do you guys remember from yesterday why that's the case? Let's not go into the details about the waves scrunching up and spreading apart and so on. Bottom line is it has to do with motion, relative motion between the source and the observer. So it's the apparent change in frequency due to the relative motion, in other words, motion between the two, of the source and the observer. When the source is coming towards the observer, what's going to happen to the frequency? The actual frequency isn't going to change, right? But the apparent frequency will go up or down. Up, right. When the source is coming toward the observer, the frequency goes up. By the way, if the observer goes toward the source, we'd get the same effect. We just don't know how to deal with that mathematically, but we'd get the same basic effect. The frequency would appear higher. Now, if the source is going away from the observer, Mackenzie asked a good question yesterday about why exactly this happens, and we gave you some information about the scrunching up of the waves and the spreading out of the waves behind the moving source and so on. Bottom line is, if the source is going away from the observer, what's going to happen to the frequency? The apparent frequency that is going to go up or going to go down? It's going to go down. It's going to sound like a lower pitch. It's that fire engine going by you where it sounds higher pitch, and then all of a sudden as it goes right by you, it becomes a lower pitch. Okay, that sound that we've heard a million times before. Now, we have an equation that describes this. Probably the most complicated equation that we've learned so far in Physics 20. Save it for the last day. FD is equal to VW over VW plus or minus VS times FS. Good news is that one's on your data sheet like most of them are. Okay, that's good news because that's a hard one to remember. But it's also hard to interpret sometimes because there's two F's in there and there's two V's in there. Tell me what FD stands for, first of all. Frequency, obviously, right? It's a frequency, but what frequency are we talking about? Is this going to be the frequency that the source makes, or is this the frequency that we perceive? Yeah, it's the apparent frequency. FD stands for the Doppler frequency, or the apparent frequency, the frequency that we perceive. Not the frequency that actually exists. You guys remember that once a sound's been made, the frequency doesn't change. That doesn't mean that the perceived frequency can't change. It just means that the actual frequency can't change. FS, therefore, is going to be the actual frequency or the frequency of the source. Both of those are going to be measured in hertz. Okay, that's tricky. Sometimes you get those two mixed up, but honestly, it's not as bad as VW and VS. We get these ones mixed up more often. You guys remember what VS stands for? Speed, right? We're not going to mix up with speed and frequency and whatever. We know that's speed, right? Speed of what? Yeah, it's the speed of the source. What do we want to do with that? VS sounds like it means the speed of sound, but it isn't, right? Because we're not necessarily talking about sound. Usually we are with the Doppler effect talking about sound, but it doesn't have to be. It can occur with any wave, including light. It's not the speed of sound, it's the speed of the source, and that's going to be measured in meters per second. VW is going to be the speed of the wave. Again, that's usually going to be the speed of sound, but you guys know that it could be speed of water, or it could be the speed of light, could be speed of whatever wave we happen to have. All right? All right. What about this whole deal with the plus minus thing? When is it plus? When is it minus? Here's the bad news. I don't remember. Here's the good news. I can figure it out. Cody, what is it? Do you remember this, or do you figure it out? Like, oh, you remember? Good, good. What is it, Cody? Okay. If it's coming towards you, it would be VW minus VS. If it's going away from you, it would be VW plus VS. I think you're right. Well, let's just go through that process of figuring it out just to make sure. If VW minus VS, that's going to give me a smaller number on the bottom. And a smaller number on the bottom is going to give me a bigger value of FD. And if it's coming towards me, then the value of FD should be bigger. So you're good. If we subtract these two, we're going to get the apparent frequency when it's coming towards the observer. If we add those two instead of subtract, we're never going to do both in the same question, right? If we add the two, then it's going to give me a bigger number on the bottom, which is going to give me a smaller value of FD, which means, yeah, it's going away from us because that's when we get a smaller apparent frequency. Two questions we had for homework. Page 432. Let's go over one or both of these questions. What do you want to do? Yep. Two. Anybody for number one, or are we good with that one? What's that mean? Is that a yes, we'll go over number one, or is that a yes, we're good with both of them? We're good? Okay, let's take a look at number two. If anybody changes their mind, we can go over number one when we're done number two. Two says, an airplane is approaching you at a speed of 360 kilometers per hour. You measure the pitch of the approaching engines to be 512. What must be the actual frequency of the sound of the engines? Speed of sound in air is 345. Hey, they give you the speed of sound in air here, but we have, if we're given a temperature of the air, we have a way of finding the speed of sound in air, right? It doesn't apply just to those air columns. It applies to everything, including this. We could say V is equal to 331 plus 0.6 times T. We don't need to because we've got the speed of sound already. But if we had to, we could. Okay, what do we got? Something is 360 kilometers per hour. What is that? V what? VS or VW? VS, the speed of the source. Now we're going to want to convert that to meters per second, right? So let's do that. 360 kilometers per hour times it by 1,000 divided by 3,600. I think it works out to be 100, isn't it? 100 meters per second. We got 512 hertz. That's going to be a frequency. Is that going to be FS or FD? The pitch of its approaching engines. This is what you're measuring. This is what you're perceiving. That's going to be FD, the Doppler frequency. We're looking for FS, right? The frequency of the source, the actual frequency. Hey, by the way, we also have the speed of sound in air. That's the speed of the wave, 345 meters per second. My equation says FD is equal to VW over VW. Cody, is it plus or minus? It's approaching us. Yes, VW minus VS times FS. Now we're solving for FS. So let's rearrange it. I told you that I wouldn't give you a question where you had to solve for VW or VS. That's too hard. Okay, that's too hard to rearrange. But solving for VFS isn't that bad. All we're going to do is take this entire term right here over by dividing. So it becomes FS is equal to FD over VW over VW minus VS. So we're taking that entire term in green over by dividing. And now it looks kind of ugly, but oh well. Let's plug in our numbers here. FD is 512. VW is 345. VW is 345, and VS is 100. So let's do this on the big calculator here to make sure that we can all do it. Let's get what's on the bottom first. 345 minus 100 equals 245. Now let's say 345 divided by that gives me 1.41. So on the bottom we get 1.41. Now let's say 512 divided by 1.41 gives us 363, 364. It's coming towards us. We had an apparent frequency of 512. The actual frequency is 364. Does that make sense? The apparent frequency is higher than the actual frequency? Yeah, it's coming towards us, right? Does it make sense that it's that much bigger? Like, this is a big difference, right? The real frequency is 364 and it sounds like 512. Does that seem reasonable? Why is it that much bigger? Yeah, Zach? Yeah, good. The plane is moving very fast. We get the Doppler effect when you got a truck moving by you on the side of the road, right? We notice it. If you've got something moving at 100 meters per second, 100 meters per second, a third the speed of sound, then you're going to really notice the Doppler effect, right? By a couple hundred hertz here. Okay, time to do our outline for the test now. Monday's test. Remember, this unit was called simple harmonic motion and waves. Let's go over simple harmonic motion first. The definition of simple harmonic motion, right? The basic definition is Hooke's law. And what does Hooke's law say? F is equal to K times X. It's actually negative Kx. If you use Kx, then that says the applied force is directly proportional to the displacement. If you use negative Kx, it's the restoring force, the force pulling it back to the equilibrium position. This is really the definition of simple harmonic motion, negative Kx. But if you mix those two up, the negative and the positive, it's probably not the end of the world. It's another way that we think of simple harmonic motion. Motion that repeats itself, right? So sometimes you're given a question where you've got the restoring force and you want to find the displacement. Use this equation. Sometimes you've got one where you've got the applied force. Okay, drop the negative if that's the case and solve for the displacement. All right? That's the basic definition of simple harmonic motion. And then we go into elastic and spring potential energy. We haven't actually talked about this in a while, right? Because even though it's part of simple harmonic motion, we did this back in our dynamics unit. I'll refresh your memory on this. Good news is, I'm not going to give you some big written response question on this. I might give you one or two multiple choice questions to refresh your memory on elastic or spring potential energy. Boils down to, look, EP is equal to 1/2 kx squared. Sometimes you got to find k by using this equation. And sometimes it's vice versa. Sometimes you got to find it using the spring potential energy equation, plug it into Hooke's law. Bottom line, the more the spring is stretched or compressed, the more potential energy it contains. The less it's compressed or stretched, the less potential energy it contains. Now, remember, the definition of simple harmonic motion, or at least the common definition that we use, motion that repeats itself. Pull it back, let it go, back and forth, back and forth, back and forth. As this potential energy increases, then the spring would slow down because kinetic energy would decrease. As this potential energy decreases, okay, the displacement becomes less, the kinetic energy would increase. So as it slows down and decreases kinetic energy, the amount of the spring stretching increases. But as it speeds up, the amount of spring stretching decreases. So as one goes up, the other goes down.